by Dr. Anna Semenkova about the barrier materials for radioactive waste storages and disposals. So, Anna, the floor is yours.
So thank you for introduction, Vladimir. And today we will talk about barrier materials for radioactive waste disposals and storages. The difference is... So one second. So everybody can hear me online? I hope so. So I think maybe you know the difference between storages and disposals of radioactive waste. It means that the difference is in the period of time, is this for the long time, but any period or forever. So that is the difference. And of course, the requirements may differ a little bit. I think we have some problems with...
Come on.
Hey, colleagues online, please switch off your mic.
Please switch off your microphones. Hear you.
We can hear you. Can you hear us? Sorry. Gabriel, can you hear us?
Yes, yes.
Okay, so please switch off your mic.
Okay, thank you. Thank you, sorry.
So I hope now we can start.
Yeah, sorry.
So when we will talk about several aspects about disposals and barrier materials for them. First of all, we will talk about scientific requirements and the processes that limit the migration of radionuclides from disposals. And we will talk about requirements for these barrier materials. And of course, we will have several examples of disposals in Russia and radioactive waste repositories. So first of all, here on the map, you can see the locations of different radioactive waste deposits, repositories all over the world. So we can see there are about more than 100 points and that differ much in their locations, in their chemical compositions, in the period of radionuclides half-life. So it is important to know unique properties of each site and to work with every site separately. But usually we have the main rules that contains the creation of multi-layer system that will protect the radionuclide and will hold them inside the repository or the site of the location. So here in the picture you can see two examples of radioactive waste repositories or deposits. Now it's not important. So it can be located on the top of Earth or a little bit underground, partly underground. Here I talk about storages for intermediate and low-level wastes. We will talk briefly about high-level wastes later. So what is dangerous? The aim of the creation of the deposits and repositories is to store radionuclides inside these objects for a long period of time, for the time of the work of this object. The most important, the most dangerous situation will have place if we'll have leakages of radionuclides outside. So when we have radionuclides inside the building, the facility, everything is okay. When we have water intrusion into this place, radionuclides will migrate. When we don't have water inside, everything is safe. So which ways of water intrusion do we have? First of all, it is rains or snow like we have now. So the water that can go from the top. And the second way is the groundwater in case if we have underground repository. So, and if we have a contact of any kind of this water with our radionuclides, we will have leakages that will go outside and to the environment. So that the main idea of any kind of disposal or storage is to prevent the radionuclide leakages outside, because it may migrate very far from this location, and it may go to water, to rivers, and it is a big pollution for the environment, and it will come to human. We can eat it, breathe it, drink it, and it will be very dangerous. So the idea of this of all this multi-barrier system is to avoid is to limit the transport of radionuclides only by one mechanism. It is named diffusion mechanism. Diffusion, I will remind you, it is the movement of concentration, in our case, radionuclide concentration, due to a concentration gradient. We don't have any movement of water. We don't have any water flow that goes through our building, through our repository. So it means that if we will have a concentrated radionuclide and have a water, we will have a small gradient, concentration gradient of radionuclides that we will move very slowly. The most important thing is that diffusion process is very, very slow. It will have a big intrusion of water to the radioactive waste location. We will have a little, very small leakages of radionuclides. The other mechanisms that is possible in case of water intrusion, it calls filtration. It means that we have a big water flow that comes into the repository, and it doesn't stop there. It doesn't slow down, and we have the same water flow that goes outside and takes a lot of radionuclides. And the activity that goes outside the repository will be very high, and the speed of the radionuclides migration will be very high. That is the worst scenario. And the idea of any disposal is to limit to stop any possible filtration mechanisms, and to let radionuclides migrate only by diffusion. That is very slow, and it will prevent any significant leakages. In case if our disposals should work for 100 and sometimes for even 1,000 years, we cannot be absolutely sure that no leakages will happen in this period of time. So our idea that we have to limit we should limit the migration of radionuclides only by very slow process. And we have, in case of if we have leakages, the very bad scenario, we have several mechanisms that will let radionuclides migrate and behave. How can the radionuclides behave in the environmental? As I already mentioned, the dangerous situation is when radionuclides migrate with water, because without water it is maybe a little bit gas flow, and it is just very small part of activity may get outside. The water The water makes it possible to migrate big quantities of radionuclides. So if we have solid part and the water is blue, and we have different kind of radionuclides that can migrate as cations and anions, that depends on the chemical form of the radioactive waste located in the deposit. It may associate with any colloid particles of, for example, of material, of soil, of something like it. It can sorb. The very big and very important process is sorption, when our radionuclides can stop. In case of leakages, they will stop in the barrier materials or in the environmental, in our soils, and so on. Our radionuclides may precipitate as a pure phase. It usually happens in case of high radionuclide concentration, and not all radionuclides can behave this way. Radionuclides can also co-precipitate with solid solutions and so on. So I think that is the most important processes that may happen in case of radionuclide leakages. I will remind you the processes that can cause the migration of radionuclides. First of all, it is filtering of atmospheric precipitation, like rains that get inside the repository. The capillary influx of moisture to the soil phase as a result of evaporation and so on. The water movement over surface when we have water flow that goes through the repository. The diffusion of anions and cations, I mentioned here they separately because we have a difference about which we will talk about later in diffusion of cations and anions. And of course, the transport on colloidal particles. And we have to provide mass transfer only by diffusion. So here is an example of repository of intermediate, I think, level radioactive waste. So what do we have? First of all, we have multi-barrier principle. We don't have just one barrier, then more dangerous radionuclides, then longer the period of half-life, then more strict rules we have to our barriers. We increase them, we should choose the materials for barriers more strictly and so on. So first of all, we always have several types of barriers that we use always for low-level waste, for intermediate-level waste, and especially for high-level waste. It is underlying screen here. Here we have as a wall and covering screen on the top. And inside we have some buffering material. And of course, first of all, our radionuclides, we put them into the package. I mean that we don't store our radionuclides in liquid form because liquid is bad and will make migration makes it more possible. So first of all radioactive wastes, they are located in solid form. After that, they are located in special containers that are located one by one for about 10 meters, it depends. And we make a bit, and there, so here's the container, just one container, we can locate them several, one on the top, and so on. And everything is surrounded, usually we have concrete walls or some concrete buildings, and sometimes the place between the containers can be backfilled with special material. And after that, we have concrete walls, some clay rock, and we suppose that our host environmental is also as a protective barrier, because in case if we have small leakage here, the big area here will protect and will prevent the radionuclide intrusion into the human environmental. It calls geological medium. So what is important? Here, the form of waste and the canister, as we know, they will work just for 10 years, maybe 50 years, less than 100 years, always. And we have examples that the steel containers and so on, they will work just for several tenths of years. In case if even for low-level waste and intermediate level waste, we have to protect environmental from radionuclides from hundreds years, 100 years, 300 years, or 1,000 years. It depends on the situation. It means that the containers, they will not work for all this period. They will be destroyed. So it means for the situation have a backfill material and all other barriers that will prevent leakages outside. So usually we have usually in practice in all over the world, we use clay screens on the top, on the side, underlying screen, and as a buffering material, because usually natural clays are used for this purposes because they're stable and they have a lot of unique properties that will prevent leakages for a long time due to their unique properties, due to different mechanisms that will stop leakages. And we will talk about it a little bit later. So for all engineering barriers, we have Okay, we have several objects and requirements for each barrier, and several requirements that are necessary for all of them. First of all, to stop leakages, and for this we should study the filtration properties, the diffusion properties of the barrier material, and it's better if our material will have high absorption characteristics for radionuclides and will not let radionuclides desorb fast. After that, our barrier materials, they should make it impossible to formate any fast migrating forms of radionuclides. So we should prevent and check our material, if it has ability to form any colloids. Because in colloids form, radionuclides can migrate very fast and very far. For example, in United States, there was example when plutonium particles were found in several kilometers from the test point, and nobody could understand how was it possible why did it happen? How could it made it possible to radionuclides to migrate so fast? And it was found that with very small, for 10 nanometers, colloids of soil, radionuclides migrate so far. Not radionuclides, plutonium radionuclides. So of course, we should be sure that barrier will be stable for the whole period of operation of the disposal or repository. So we should check the material stability. And in this case, clay materials that are very stable, that are very long, that are very old in case of geological times are very suitable. And of course, we should check the resistance of every barrier materials for tectonic movements and any seismic activities, and we should prevent their plasticity. And of course, not the least, materials should be very safe in case of fire or any explosions, and they have to be acceptable by cost, by the logistics and technology of their usage and so on. And usually, as I've already mentioned, it is common knowledge that we use nature materials like soil, sands, and clays, and especially bentonite clays. So why do we talk about bentonite barrier materials and bentonite clays? First of all, what is a bentonite clay? It is material, nature material, first of all. It is rather widespread, and it is made from aluminum and silicium octahedrons and tetrahedrons. Here the picture of it. And between lower, this tetrahedral, octahedral, tetrahedral, it is called TOT layer, or layer, just layer. The clay particle consists of many layers of TOT, and they have an interlayer space here. And it is possible and here in this interlayer space, water can be held. Water or any cations. It is very important. Why is it possible? Because we talk about nature materials, so we have some substitutions in our octahedrons and tetrahedrons, and we have a small charge. So it means that aluminum and silicium in our structure, they can be substituted by cations of different charge, and we have a small charge on the layer. It calls layer charge. In case of bentonite clays, it is a negative charge, small negative charge. And to compensate it, in case of if we have water in our system, we have the compensation happens. Sorry, can you please turn on your micro? We can hear somebody.
Film Monopula, please turn off your microphone.
Я уже сказала. Вот так вот. Okay, let it be so. Water and to compensate the negative charge that is located here or here, it is necessary. The compensation happens with the use of water and cations that always we have in water. In case of not only as cations, some of our radionuclides can be used. So, and then due to the possibility of water intrusion here, the bentonite clades, they have a unique specificity of swelling. It means that several molecules of water may be located here, and they will, this water, it is stable water that cannot move far. It is located here, it is stopped here due to the forces and the clay forces, electrostatic forces that are observed here on the surface. So the possibility of swelling, what does it mean? That in case we have small, here is a bentonite particle, not just particle, here's an example of bentonite particles, and here is a specially pressed bentonite material. And in case if we locate it into the water, it swells, the size increases much. And it is very favorable in case of our disposals. If we have any leakage, our water sorbs on our material. We will not have water intrusion inside or outside, swelling. Very good possibility, and it prevents filtration. You should notice it. And in case of long-term stability, of long-term exploitation of our disposal, it is important to notice that bentonite clades have ability for self-healing. It means if we have any cracks in our material, maybe they were due to high temperature, they were dehydrated and we have small cracks. But in case when we have again water, swelling, no cracks, no leakages. So of course, the bentonite clades are natural material and they're very stable for long periods of times, for million years. That is much longer than the period of radioactive waste disposal exploitation. Radionuclides have high sorption properties, and in case for many radionuclides, low desorption properties. And bentonite clades have very low diffusion properties. I mean that low diffusion, it is very good because, okay, just believe me that when we talk about diffusion properties, then lower, then better. High diffusion, it means high speed of diffusion. Then lower speed of diffusion, the lower speed of migration of radionuclides. That's good. And here is another example of a structure of a clay particle. So here we can imagine that here's tetrahedrons, octahedrons, tetrahedron, octahedron, and interlayer space. And we have different possible parts where radionuclides can sorb. How can they behave? So first of all, we have here on the lower we have a negative charge. So here can be sorbed cations, plus charge here, and also we have hydroxides groups on the sides, aluminum or silicium sides, and sorption of some radionuclides can be here. Here's another example of swelling. So we see our structure, our crystals, they make aggregates, and when we have water intrusion, they make small aggregates of several particles. Then more water comes into the system, that becomes bigger and bigger swelling. And here's an example of swelling. As I already mentioned, bentonite clades, they have very good swelling properties. It is due to the existence, in the presence, in their mix, in their composition of smectides or montmorillonides. They have very good, very high swelling properties. But because we talk about nature materials, we cannot say that bentonite clays, they consist only from one material, only from one clay mineral. No, we always have a mixture, and our idea is that to find the best mixture that has the biggest part of swelling swelling clays in their composition. We have here with just several types of widespread clay minerals are listed. So we have several types of clay minerals that with the smaller swelling properties and smaller charge. It is elite, micas, kaolinite, and so on. So the more then the bigger part of smectites we have in our mixture, in our bentonite clay, then better. So we will talk again about diffusion. So here is an image that about clays, how clay particles or some environmental or maybe clay rock. And what is important? Now we can perform diffusion properties and measure the diffusion parameters in our laboratory. So we have several stands for it. So what is the idea? We have a sample of clay and we have a radionuclide here that move here, flow of radionuclides here, and flow of pure water on the other side of the sample. And we can measure the activity in pure water. And when we will find our radionuclides in pure water, due to this parameter, we can find the diffusion characteristics of the material. So here we have an example of tritium water and uranium, cation of uranium. And you can see that different radionuclides can migrate with different speed or can diffuse with different speed. So here we have an example for several materials with varying montmorillonite content. And you can see that then here is the part of montmorillonite, and here's the biggest part. And here we studied the diffusion of tritium. It is usually called as non-sorbing radionuclide, and the chloride. So what is important that then when the proportion of montmorillonite in our sample increases, the diffusion coefficients decrease. It is very good seen for chloride especially, and for tritium also. After that, we can notice that if we make a sample with bigger density, then diffusion decreases also. And it is also necessary to note that when we have a big part of montmorillonite, the diffusion of negatively charged chloride is decreased. It is very important, and we will have this situation for all other anions. For cations, the situation is not so good, but we'll have we'll have sorption for cations that will prevent migration. So here is so you can see that bentonite clays, they prevent any filtration mechanisms of water radionuclide migration. They're very good for diffusion, so they prevent the very small diffusion characteristics, and they will have a very good sorption characteristics. What does it mean? You see that anions will stop. The anions migrate by diffusion mechanism very slowly, but in case of cations, it doesn't work. But cations, they can be sorbed by negatively charged parts of clays. So, we have different types of cations. We have different. They have different mechanisms of their sorption, and it is necessary to study each of them separately. Anyway, for every disposal, it is necessary to study several site-specific, several conditions that may influence to the barrier properties, to the speed of radionuclide migration in case by diffusion, by sorption, and so on. So first of all, it is necessary to know the radionuclide composition in the disposal. It is very important to know the solution compositions, because in different, I think I have an example here. Here's the natural water from different sites, and you can see that they change pH, this composition by the main cations, the stable cations, not radionuclides, just the composition of water can vary very much. After that, it is impossible to know is it aerobic or anaerobic conditions. It is we should know about microorganisms that can prevent or avoid increased speed of migration of radionuclides. We should know that here. Yeah, here's the example for aerobic anaerobic conditions. In case for uranium, that is usually it is very widespread material that can be located in deposits. For uranium, in case of aerobic conditions, uranium can form complexes that do not sorb very well. And in case if we have a lot of water or we have oxidizing conditions, it is possible. We should remember that uranium and several other radionuclides will migrate faster than in case of absence of aerobic conditions and so on. Here's the example of heating. We should know that if we will talk about high-level waste or intermediate level waste, it is possible they will heat due to the radionuclides decay in the waste, and the increase of temperature may occur and the temperature may increase sorption of radionuclides. So I will very briefly talk about sorption of radionuclides. Here you can see that different sites are possible for the radionuclide sorption, but different kinds of radionuclides, different types, they may sorb by different ways. I will skip it. And I also want to mention that here's an example of bentonite clay. And here we have a pure clay and clay that has 3% by mass of goethite. And you can see that in case of neptunium and other lantanides and actinides, it may be the sorption may increase very much when we add some admixtures. Small parts of admixtures can change our can increase our sorption very well. It is very interesting and useful for our for us. And the last example about scientific side of our talk today are that here we have clays from different deposits in all over the world, and here's the example of cesium sorption on these clays. And you can see that here's the concentration of cesium and the distribution coefficient. You can see that on different clays, the sorption distribution coefficient differs very much. And it means that we cannot take just any clay. No, we should choose the better one. Because here, this difference, it is very, very big. And after that, when we have, what for do we do? Why do I talk so much about diffusion, sorption, and so on? We can, from our experience, we can have some parameters like distribution coefficient, diffusion coefficients, and so on. And we can make a thermodynamic modeling to be sure that our material, that our construction of the deposit will be safe for the period of time in case of any, I don't know, anything will, in the worst scenario that can happen, everything will be safe. So we have the characteristics of barrier materials. First, we've talked about functional characteristics that for absorption, diffusion, swelling, and so on. And after that, then also it is important that we should make it possible to locate our material in the form with these properties that are necessary to work them very well. So granulometric size, mineral composition, and so on, density of the material. You should remember the example of diffusion, because with different density, we have different properties. Then bigger density, then better, usually. So we should check our material for flexibility, deformation, and so on. So you should remember it. And again, what do? We have to limit our radioactive waste packages to contact with environmental waters. Here we have types of different radioactive wastes due to the IAEA classification. Then lower the activity of radioactive wastes, then they can be located on the top and just below the ground level. Then more dangerous the waste, the bigger concentration of radionuclides and so on, then deeper we locate them. In case of high-level waste, we locate them in depth of 5, 8, 1,100 meters or up to 1,000 meters. So 1 kilometer depth. What also I want to tell you that we have strict rules in case of high-level waste deposits for materials and so on. But when we talk, no one country has strict rules for how to choose the materials for barrier materials for intermediate and low-level waste storages. So every time when we have an idea to make a storage, we create something special, something for this site. We don't have the unique example how to do it. A lot of researchers, they were devoted to the study how to make it safe, the high-level waste repositories. But what is important for us, we can be guided by the rules that were observed from the studies made for high-level waste repositories, and we can use these rules and this information for our intermediate and low-level wastes. Here's an example of multi-layer barrier system. Here we have for high heating container waste and for low-level generation waste. So here's an example for high-level waste radionuclides repository and for intermediate waste. Here's the example of high-level waste that is the system of drills that are located deep on the earth, 500 meters and deeper. Our radionuclides, they are located in special container. In different countries, different materials of containers can be used. And what differs, the biggest difference in case of barrier materials, in case of high-level waste repository, it means that the buffering material, it should be not just for field, it is pressed. We use like blocks for because we need the biggest density of our material. So that is and here you can see that here we have on the picture, you can see the pressed forms of our clay. And it is made because for high-level waste, we should justification the safety more than for 100 years. 100,000 years, and in some countries up to 1 million years. We should demonstrate that our repository will be safe. So here are several examples of laboratories that study materials for high-level wastes. But I think I will skip it and we will talk more. So yes, and it is interesting that for high-level waste, we can find more than 1,000 papers devoted to this, to the choose of material, to the studying of their properties and so on. If we will try to look in the system for intermediate level waste or low level waste, we will find just maybe several tenths of publications. So that's why it is important that we can be guided by the rules that were found for high level waste, and we can use them for our intermediate and low level waste. Here's the example of low-level waste radioactive disposal. It is located near Earth. It doesn't have not very deep. It has several containers inside, a number of containers, some concrete walls, backfill material around, and it is covered with topsoil and so on. Or maybe not just topsoil, it can be several layers of material. Again, the picture you've already seen, and here are the examples of the materials that can be used for covering screen or underlying screen. It is called bentomates, and the material is made by two layers of geotextile, supporting and covering layer, and between them, the granulated bentonite is located. It is pressed and very good, and it is very comfortable to use them. You see, it looks like, I don't know, about 1 centimeter, 2 centimeters of material, and it looks like paper or something like it. It is very simple to use. Here's the example of underlying cover that is made for any kind of disposal, and it is also can be located on the top to prevent water intrusion from the rain. Here, after that, we have several examples of containers that have radionuclides inside. In Russia, all over the world, there are different types of containers, and in Russia, we have different types depending on the activity, on the radionuclide composition, and so on. Usually, we have metal containers or reinforced concrete containers. It looks like this. It is about 1 meter or 1.5 meters, and we have a different type of containers. Here are just examples. Some of them are returnable, some of them non-returnable. It means that we put radionuclides inside our waste, we put it on the disposal, and we dispose them in container. In some cases, it is for low-level wastes, or very low-level waste. It's possible to use container just as a bag. You put our waste, put it on the place of disposal, take our radionuclides, and we return our container back to the facility. And we can use the one container several times. But usually we store radionuclides in the container that was used for the transportation. So here are the examples for containers due to their size and the capacity and so on. And here are the examples of radionuclides repositories and disposals. Here's the example of very low-level waste located in Sweden. You can see the concrete blocks downstairs, containers that are not very specific. They're just usual containers that are used for transportation, just metal containers. And in the scan, you can see here that they have small underlying screen, some layer of covering layer. Here located our waste, and we have a small covering sheet and buffer material on the top. So we can imagine how does it look like. In some cases, for very low-level wastes, it is not very good. And in the last years, as I know, this practice doesn't used. But for the very old deposits, some waste can be located just in bags, not in special containers. And actually, you should, if we have a very old disposals or repositories, we should remember that, and we should always check and monitor the situation about the disposals, to be sure that we have no migration. In case we will find radionuclides close to the site, it is necessary to take it all off or to make any additional barrier systems around this place. Here's the example of on-top disposal in Europe, and here you can see the metal buildings around. So we have a concrete building and special metal construction that will prevent water intrusion and will prevent the spoil of these concrete walls. Here's another example. In Belgium, there were different places, different disposal places that are surrounded by soils and sands. And on the top, we always have crushed rocks and bentonite and some clay materials. And usually it is surrounded by the green grass. It looks like a usual like footballs, some nice place just for walk. this I just want to I have a lot of pictures. I just want to show you that in all over the world that we use the same principles for different types of disposals and repositories. Here we have the Japan example for intermediate level waste that's located underground, and they have containers that are surrounded by bentonite clays as a buffer material inside the disposal. Why is it common to use bentonite as buffering material? That we will stop of moving of our containers. So it just, in case if something happens with here or with the construction where they're located our containers, if all containers are surrounded by buffering materials, containers will not move, they will not fall down, and it is very good, especially in conditions of Japan when we have earthquakes and so on. And here's very interesting disposal of the first experience of radioactive waste redisposal. In Hungary in 1950s, 60s, there was a special place, Solimar site, located very close to the Budapest, the capital of this country. And in several, it was found that there were leakages of radioactivity from this disposal. And what was done? It was necessary to do something, maybe to make a new barriers or something else. But because this place is located very close to the capital of the capital, it was made another decision to remove all the radionuclides, all our waste, to another place located in the there where just not so many popularity were lived. So they created a new disposal. Here's the, how does it calls? And they made a final isolation of radioactive waste, and they make a big disposal where were located all waste that were located in the Solimar site, and the place that was enough to storage new radioactivity that was accumulated during the activity of I don't know. There was a medical center that was working with oncology and with the radionuclides and so on, and with the atomic station and so on. And here's the example of the created site, of the new created site. They first of all, they created it in 2000s, and when it was fulfilled, they built the new one in 2012. And here's how does it look like today. Because first of all, when it was in Solimar side, there were just trenches which were filled with waste without any special barrier systems. So nowadays they have very modern system with they used the best knowledge of that was possible. Another bad example of storages that was in United Kingdom. Here we have Sellafield, and close to the Sellafield side there was a Drigg, the storage of low-level waste. It was located very close to the sea, and it was found that they found that there were leakages of radionuclides to the sea. What was done? They were they made a new repository. They used a multi-layer system of barrier system, but after 15-20 years of exploitation of the new repository, it was found that containers that there were leaks, and that they were found that there exists the degradation of metal containers, corrosion, the water was in containers, and so on. As far as I understand, it is due to the closeness to the sea, due to the water, the sea water, it is very aggressive. But and you see that even in it it is necessary always to control what happens in any of our repository. After that, we should control and ask ourselves, is it safe or not? Is it necessary to make something better? Even if we think that is new repository and everything is okay, maybe we didn't know something that will let radionuclides migrate faster than we it's supposed to be. So we should check, we should control, and we should always know that maybe it will be necessary to make something better, to remove it, or to add any kind of additional barriers. And I will very briefly talk to before. Here we have the usual deposits, examples of usual widespread disposal and repositories. But sometimes we work with very special radioactive storage facilities. Here's the example. These sites, they cannot be relocated, and the only one decision can be made. It is called on-site disposal. It means here's the example of a reactor, uranium graphite reactor, and it is very big building, about 30 meters, 40 meters, and 60 meters. So it is impossible to remove them absolutely. So what was made? The decision was to demolish the on-ground building and backfill all the rooms of the reactor by backfill material on clay material. And yes, it was realized. Here the experiments, a lot of experiments were made to demonstrate that this method, it will be safe, will provide the safety we need. Here's the example of cavity-free backfilling. Here you have 6 or 9 meters, I don't remember, and here about 2 meters here. So, and we color, not we, specialists, they colored the material, and to make sure that they have cavity-free backfilling. Here's the photos made from the schema of the reactor and how that was backfilled. So very big room, and everything is backfilled by clays. Another example, it is conservation of basins. In Russia Federation, we have a lot of examples. In the beginning of atomic energy, when nobody could understand how dangerous is it, some radioactive wastes were stored in basins, special basins. Some of them have protective layer or were located just on ground. Some have concrete walls or something like it. It was just water with radionuclides. Sometimes very aggressive water with pH from 3 to 12. Not usually 7, no. And what is important, usually we have special pulps, material, it is like soil or something like it, that could sorb radionuclides very well, and the water was rather pure. Radionuclides sorbed on this material, soils, or I don't know how it depends. Their composition depends from the site, and biggest part of radionuclides was sorbed on the pulp. So what was made? So the water was moved away, and the most activity was located in the pulp. So the water was moved, and the basins, they were the special top screen was made on the basin. So no intrusion of radionuclides by wind, by rain, or something else. So it was prevented. And nowadays, it doesn't look like a basin. It is just the usual ground for walk or something like it. Here's just one example. Another example, yeah. If we have, here the example, first of all, I should notice that we didn't have any leakages from the underlying, from the bottom of our basin. In case if we have leakages, we should make special walls around around our basin or underlying. We can, it is very underlying, it is very hard, but it is possible. So usually if we want to make a wall around the basin, there are two ways are possible. First of all, it's called wall in soil technology. So we make a big trench tunnel around our basin, and we backfill it with our clay material, usually bentonite clays, but different content of montmorillonite. And after that, sometimes it is possible to make concrete, to add concrete there, and so on. It depends on the basin, on the situation, on the radionuclide composition, on the technical possibilities, and so on. And another possible way is to make a vertical injection. It is called jet grounding technology. What happens? We make a hole, deep hole up to 30-50 meters, and we under big pressure, we inject our material. I mean something, usually it is based on bentonite clays, but with special admixtures. And we inject our material. It is mixed with the material surrounding here, and we make columns one by one, and they not in the distance, they not on the distance, the columns located not on the distance between each other, but they are overlapped. So we can make a screen around the basin, and using the same way we can make underlying screens. So here's the example of I think it's somewhere basin that were surrounded by Chelyabinsk, that was surrounded by jet grounding columns. And here's the results of modeling. What will happen? How far will radionuclides move? In first case, if we will not make any special construction, so we can see that uranium will migrate very fast, very far, and we will find uranium in the river. In case if we will make columns 1 meter, the uranium will have just small leakages out of the plant. But in case if we will make just 3-meter vertical barrier, that we will be lower than the water layer in this place, so we will prevent significant leakages of radionuclides. And here's the example what will happen in the close the basin located very close in 1,000 years. Here's for 400 years this place, and here's for 1,000 years the same. That if we will make columns that will surround our basin, or radionuclides will not move to rivers, to the environment. Another example, the same. So how far will radionuclides move in case of if we will not make special constructions? So, and I think I will finish. And nowadays, Moscow State University works in 2 big programs that are devoted for barrier materials, for creation of them. First of all, it is a program for technological and scientific support to select the barrier clay materials for storages and disposals of intermediate and low-level wastes. And the second big program, it is made for high-level wastes disposal that will be located in Nizhnekamsky Massif. So we have a practice in all kinds of barrier materials. And I want to thank you for attention. I'm ready to answer questions if you have them. If no, I think we can make a 5-minute break. Or you will have lunchtime, as far as I understand. Yes, до скольки? До скольки, скажи?
Так, если они 15, сейчас вы поднимете.
So in a few minutes, Vladimir will come and will tell you about how long break will you have, because maybe due to the problem with the bus in the morning, we will not have time for the second lecture before lunch.
No questions? Yeah, one question. So just wait.
So I'm asking about the previous, I think, slide. The name of the program for the model, yes. The name of the program for modeling.
I'm not
system.
sure using which program this modeling was performed, because there are several programs are possible. I think that was Nympho or Gera, the programs that are that we use in Russia.
Okay.
But I know that there exist even free programs that can make it possible to model the
Model this,
migration.
yes.
Yes, but it is very hard.
Yes. Okay. Thanks.
You're welcome.
Any more questions? Are they in chat? No? Skip. Сообщение.
So thank you for attention.
So thanks again. So due to the shift of the schedule, we propose that now we will have a lunch. We will come back at 1:30, so 1:30 here. We have these coupons for the lunch. Please take them. And we will continue at 1:30. Yeah.
А слышно? Что, меня слышно? Слышно откуда, если что? Оттуда, хорошо. Да, она, по-моему, уже открыта. Я открыла ее уже. Нажать надо. Мгм. И перекликашкой. Да. Я просто не Hello, dear participants. Let me start the lecture about the processes to be considered in the modeling of radionuclide migration. My name is Anna. I'm working here. I'm a radiochemist, and today I will present you the lecture about modeling, but mostly modeling in chemistry. And I hope you will enjoy it. Okay, as I understand, the main topic of your school is the waste disposal, yeah, and reprocessing of waste. And of course, when we're talking about waste disposal, we need to understand that sometimes or somehow radionuclides can migrate to the environmental, and it's the bad situation, but in fact it's sometimes happen. And when radionuclides go to the environmental, they can interact with all that they met, for example, environmental minerals, soils, water, of course. And if we want to predict the migration of radionuclides in the environmental, we need to understand how the radionuclides interact with this component. And another thing that I need to say that when we, for example, create the new disposal, we need to understand if the disposal is safe or not. And how we can understand safe or not this disposal, we need to predict how radionuclides may migrate from the disposal. Of course, we hope that any water will come to our disposal, but when we make some project for this disposal, we need to predict how it will be if water will come or something, for example, some dangerous situation may happen in the disposal, and again radionuclides may come to the environmental. From the chemical point of view, actinides or another radionuclides, when they come to environmental, they may interact by different chemical reaction. And here's the list, the most important chemical reaction concerning to the radionuclide behavior in the environmental. First of all is the sorption reaction, because in any case, when we have radionuclides in the environment, we have small amount of radionuclides and a big amount of minerals and of soils. And of course, the sorption is one of the most important mechanisms of the interaction. And another mechanism is complexation, redox reaction, and solubility. And today I will explain all these four kinds of the reaction, and I will also explain how we can predict, how we can model this reaction in our predictive modeling when we're doing predictive modeling. I will start from the complexation because it's, from my point of view, is more easy compared to other. And when we go, when we talking about the complexation, we can divide this complexation to different groups. First of all is hydrolysis, because we have a lot of water, and hydrolysis is the first reaction which play important role when radionuclides and actinides go into the environmental. And it's maybe interaction with inorganic ligands, with organic ligands, or with something like bacteria, or maybe even other more bigger microbiotics and so on. For the explaining for the description chemical reaction, there is a mass law equation. It's one of the most important law in the chemistry. What we can see here is that we have precursors of the reactions A and B and products of the reaction C and D. And when we have this equation, we can calculate the constant of the reaction is K, which equal products of the reaction divided to the precursors. And what the main idea of this equation is that if we know the K, and if you know the sum of A, B, or C, or D, you can calculate this equilibrium in any time. And the main important information that we need for the modeling, it's usually K. If you know the constant, you can predict the reaction. And the main idea, if you want to calculate some reaction, you need the constant. This picture presents some different representation of this equation. Sometimes you need to account also influence of the ionic strands. Is a gamma coefficient can help you. It's very important for the high salt solution, but all of this equation is the same in principle, but they have a different particular situation for the using. And here's an example. For example, we're talking about hydrolysis plutonium-4. We can write the first reaction when plutonium-4 interacts with water and the first hydrolysis reaction products are produced. And this is the K constant of the equation, constant of the reaction. And the second step of the hydrolysis will be have this equation. And again, another constant we will write. If you know this constant, you can calculate in which form of particularly plutonium-4 present in your particular situation. What I need also to say is that sometimes you can find not K, but beta. And beta is also the constant of the reaction, but they use usually it's used for some interaction with inorganic or organic ligands. It's called the stability constant. It's actually similar to the usual constant, but it's for the ligand, it's maybe easier to compare because the stability constant increases when stability of the complexes increases too. But if you know the beta, you can calculate the K, and if you know the K, you can calculate the beta. It's not the big problem. If you sometimes met the beta, it's not to be a fear for you. This source I can advise to use it's created by Nuclear Energy Agency, and they published a lot of books about the thermodynamics of actinides in particular, but also thorium and technetium and iron. Why they do it? Because, as you may understand, actinides is not so really analyzed or not so really studied materials. That's why thermodynamics for actinides it's very limited, and sometimes it's not good. What they do, they search the literature, they search the papers, and they advise to they invite the experts to read these papers, and they found the most reliable constant and put it to their books. And for sometimes, for some reactions, you can find that in the books written that there is no any good constant for this reaction. And you need to understand that this is uncertainty of your model if you didn't know the constant of the reactions that you want to account it. But if there is in the book they're written that is okay, the constant is good, and they have a lot of papers about the same with the same values, it's okay, you can use it to the modeling. And then you can use some software. There are a lot of different kind of chemical software. From my personal point of view, this one is the most friendly, user-friendly. That's why I advised it to you, but in fact, you can use different one. You can put the constant from the books or from the databases and then calculate the behavior of the system in any pH or concentration and so on, like this one. Okay, then if we go to come back to the actinides, and as I started from the hydrolysis, first I need to say that when we come talking about actinides, you need to understand that actinides usually may present a different oxidation state. It's not like lanthanides. Actinides is quite difficult story. And as you see that any of actinides may exist in different oxidation states. The most stable is 6 for uranium, 5 for neptunium, 4 for plutonium, and 3 for americium, but actually they may have redox transitions. What you need to understand more, that in different oxidation state, actinides usually present in different ions. For example, in case of 3-valent actinides, they present in the form of ion actinide 3+. When we're talking about tetravalent actinides, they usually present in cation actinide 4+, and formal charge and effective charge is similar to the charge of the cations 3 and 4 correspondingly. And it's very high charge compared to, for example, sodium or strontium and so on. That's why actinides in 3 and 4 valent are usually is more active to the all chemical reaction. When we go to actinide penta and hexavalent, they form so-called dioxocations, actinyl or actinyl, for example, uranyl or uranyl or neptunyl, and the formal charge is less than, for example, 5 and 6. You see the formal charge +1 and +2 correspondingly, and the effective charge is +2.2 and +3.2. I tell you this information because it's very important for chemistry. You see that complexing activity, affinity, or for example, hydrolysis activity or any other chemical activities usually have correlation with this charge. And you see that pentavalent actinides is less active to any chemical reactions, while tetravalent or hexavalent is very active to any chemical reaction. What we see in the results, for example, if you want to compare hydrolysis of plutonium-4 and plutonium-5, we see the quite different pictures. In case of plutonium-4, plutonium-4 start to hydrolyze at pH less than 1. You see that it's firstly plutonium-4, when increasing pH is plutonium OH 3+, and then it's second hydrolysis and third hydrolysis, and it's even fourth hydrolysis. In case of plutonium-5, which present as plutonium O2+, it's not hydrolyzed before pH 8, and only at pH higher than 8, it's starting to hydrolyze. That's why if you know the constant, or if you know that even chemistry properties, you can somehow predict the behavior of these cations. If we will go later to the complexation, we go to the actinide halide complexes. And in this case, I need to say that halide complexes is usually not very important for actinides, maybe only except for the fluorine, because the fluorine have a very high complexation constant with all actinides, but for another it's not so important for the different environmental system. It may be important only if you have, for example, very high concentration of fluorine, or somehow it's maybe some bromine in your solution. If you have a very high concentration of these components, maybe you need to account in this reaction. If we will go to another inorganic ions, we can make a trend for the complexation. And you see that the most important ions, it's OH and carbonate. And the second place is for sulfate, phosphate, and fluorine. And the less important is fluorine and the nitrite. It means that if you describe the environmental system, you firstly need to describe hydrolysis. You need to describe interaction with carbonate. If you have sometimes sulfate or phosphate, you need to account it too. And for other, you may skip at least at the first time of the modeling. And again, as you see that for different oxidation states, for example, plutonium, the constant will be different. And again, plutonium-4 is have a highest constant, and this means that highest affinity, and plutonium-5 has the lowest constants with a lower affinity to the reaction. About carbonate, I need to say, maybe everyone is you know that, but the carbonate may come by dissolution of CO2 in the water from our air. And the solubility of CO2 is different and different with pH values. And with pH higher than 5, CO2 start to dissolve in the water, and you see that with increasing pH, concentration of carbonate in solution is increasing. And if you, for example, talking about some ponds, on some rivers, on some lake, they are in particular in constantly interaction with air, and carbonate will come to the solution and dissolve, and carbonate concentration will increase and increase up to the linear of the modeling. And that's why if you have a system with equilibrium with air, you can calculate how much carbonate you will have in solution. And what we see, for example, for plutonium-6, that if you have just plutonium-6 and water, you will see the hydrolysis, of course, and it will start from pH 4, for example. But if you have a system with plutonium, water, and CO2, this means that just plutonium, water, and air at pH higher than 5, you will see that the carbonate complexes of plutonium will dominate even up the hydroxide complexes. Carbonate species is very important not only for plutonium, it's mostly important for uranium actually, because uranium is very active to the carbonate speciation, and for environmental system is very important because it's affected to every reaction of uranium in the environmental system. It's also important for strontium, for neptunium, and for plutonium, but mostly it's important for uranium. And on this right side is it the sorption curve of uranium onto clay minerals, but it's the same on the sand, or the same on the iron oxide, or the same on the other minerals. You see that up on pH 7, the sorption is decreased, and it's very dependent on pH value and on its carbonate concentration. And in fact, uranium is very uranyl is very mobile cations just because of its carbonate complexation that prevent any sorption reaction. What we need also understand that except the inorganic ligands in our system, we present some natural organic ligands, and it's a much more difficult story because organics may be different. Sometimes it may be organic from the waste composition from cement or something like that, and it's let's say engineering organic or not natural organic, and sometimes it may be natural organic ligands that may have different composition. And in fact, for this story, science is not so good. You can even look to the NEAR database, and you will find that for organics complexes with actinides is much less studied and much less information we have. And if we can go even deeper, it's not only organics like complexes, it may be some siderophores or some humic substances which have been present as different. complex composition with different complex functional group. They may lead to the redox reaction, some oxidation reaction. And in fact, if you have in the system humic substances or natural organic matters, it means that your system is more complex and you need to go to detail for the understanding the behavior of radionuclides in with these substances. When we finished with complexation and moved to the redox reaction of actinides. And again, you see the same pictures from the different oxidation state. And this means that sometimes redox may change during the interaction with environmental. It is, again, sometimes it's this reaction may involve by bacteria or some microorganism, but sometimes it may results of interaction with organic substances too. And of course, I need to say about plutonium because it's one of the best for me elements, of course, but it's also very interesting elements because they have a very interesting redox chemistry. You see here that transition to the different oxidation state of plutonium have a similar potential. You see this here is around 1 volt, here's 1 volt, here's 1 volt, here's 1 volt, and here just a little bit higher than 1 volt. What this means that plutonium usually may present in even 4 oxidation state in one beaker, for example, and can easily change the oxidation state just for the staying on the beaker. You can leave it like plutonium-4, and after 2 weeks, you will have a mixture of different oxidation state. And this is complex situation. It's not the same for uranium or for plutonium, but sometimes it's happen also. But for plutonium, is the most complex situation. But in general, when we, it's the meaning of some big scientists that plutonium is the element of surprise. It's true because sometimes it surprisingly changes the oxidation state, but if we're talking about the environmental system, we can say that in oxy condition, plutonium mostly presents as plutonium-5. And when we go to underground condition, it's mostly present as plutonium-4, plutonium-3. And if we come back to your purpose about, for example, creating of nuclear-based waste disposal, if you understand that you are talking about underground waste disposal, you may predict that plutonium mostly will present as plutonium-4, plutonium-3. But if you're talking about some remediation of soils or some remediation of ponds or remediation of lakes, you may understand that plutonium may present in plutonium-5 and plutonium-6 oxidation state. Here's papers, very old papers, but it's very good, that plutonium was found in sea water. And in that case, it was found that in water, plutonium presents in plutonium-5 and plutonium-6 oxidation state, but when plutonium connected with some solid phases, with colloidal particles, it's plutonium-3 and plutonium-4. It's again the example that plutonium firstly may present in different oxidation state in one place. And second thing is that, plutonium-5 and plutonium-6 is more mobile usually, but plutonium-3 and plutonium-4 usually less mobile and connecting with colloidal particles like organics or like inorganics. Now we move to sorption reaction. As I said, the sorption is, from my point of view, is the most important reaction concerning to the environmental behavior. And in this case, we can see the role of the different inorganic minerals which can absorb the radionuclides and actinides in particular case. And the first place is iron oxides. It's usually not so widespread, but even 1 to 3% that's present in soil or clays even may influence on the sorption and may dominate the sorption of different actinides. Clay minerals is also demonstrate a good sorption properties. As I understand, you have the selection before me about the clay. And quartz is actually not very good sorptionability, but because it's widespread, is everywhere. Sometimes we need to account its sorption onto quartz too, because it's dominating in mass in case of the minerals. And sometimes you may found in your system manganese or titanium oxides, and it's also very good sorbing properties have. That's why they may influence on the reaction. And if we talking about the modeling of sorption reaction, for the moment there are two different approaches that usually people use for the describing the sorption. First is KD approach. It's more simpler. It's simplest and quite easy to understand. We just do the experiment, determine the KD of the reaction, its coefficient, distribution coefficient between the liquid and between solid phase. And then we use this KD and apply it to the modeling. It looks very simple and easy, but in fact it's from my point of view is not good, because this KD can describe your system only in the same experimental condition. It cannot describe the system with changing the pH, with the changing the carbonate concentration, with the changing the, for example, sodium or radionuclide concentration. It's KD have not predictive forces in all cases. That's why KD it's easiest, but it's not really working for of course for the nuclear waste disposal. You need to assume in the different ways how it will place, how reaction will do. That's why you need more information than just KD. Another approach is so-called surface compensation modeling, and in this case we need to determine the exact processes and make it thermodynamic modeling. How it looks like, for example, we have some cations or anions of radionuclides, and they interact with our surface. Usually surface have a functional group on the surface. For example, in case of iron oxides, S on this picture is means its surface, but in case of, for example, iron oxides, it will be iron groups. In case of clay minerals, it will be silicon or aluminum groups. And when our cations or anions interact with this functional group, we can write the reaction similar as we do when we present complexation in organics. And then we can calculate again the constant. It's have a similar view as we do for the complexation. However, you see this factor that describe electrostatic interaction of our cations or anions, that is charge, with this plane that is also have some charge. There is electrostatic factor that can describes the electrostatic interaction of cations with the surface. But in fact, if you have this constant, you can use it and you can make the modeling. Now this option is similar to the complexation. The worst situation that compared to the complexes, there is no any good, reliable books with the constant. Unfortunately, for the moment, NEA was started this option project, as I understand, in early 2004 and 2005. It was started option project, but they did not publish any book because different scientists still different view on this option reaction. But in any case, you can, for example, go to these databases, Rosendorf, They made from Rosendorf, Justin Rosendorf. You can go to the website and you can find these databases where you can choose a mineral, for example, quartz or hematite. In this case was goethite, and then you can choose the ligand. And you can choose any radionuclides that you may be interested. For example, in this case, it was Neptunium, yeah. And just to find the different reactions that were published anywhere. You see that there is a reference. It means there is 1, 2, 3, 4, 5 different papers with 10 different reactions. You see there is no any reliable or not reliable. You need to understand by yourself which reaction do you prefer to use in the modeling. But in any case, the database have to find every reaction. And I can advise it to you. If you don't have the constant reaction in the database, or you not rely for this, you may calculate the constant by yourself. For these reasons, you need to perform the sorption experiment. And then you need to calculate the constant of the reaction. You can use different, again, software for this optimization. And but what we need to say is that there are a lot of variables, there are a lot of parameters which you may vary. For example, stoichiometry of the reaction, how you will describe the reaction of particular sorption. You may vary the density of the surface species. You may assume that only one sorption, one type of sorption site presents on the surface, or you may think that it's maybe two different sorption sites. And you may assume that, for example, americium in this case may have monodentate complexes like here, or bidentate, or tridentate, and so on. This variation is still present, and what, for example, we in our lab may advise to you is that you need to you need to do experiment in the wide range experimental condition. You may to have sorption isotherms. You may have sorption pH dependencies. You may also find literature data, experimental data for this option, and then you can model it and found the thermodynamic constant. For example, it may be also sometimes working when you plot so-called linear free energy relationship. You see there is a hydrolysis reaction. This is a sorption reaction, and they have a linear equation between each other. And if you plotted this for example, different cations like it was here, you can use it for predictive modeling. For example, if I want to understand which constant will be of plutonium sorption, I may use this equation. I may put, I know hydrolysis reaction of plutonium. I will put it and calculate constant of the sorption. Of course, it's just a calculation, but for some prediction, it's may work perfectly and can help you to describe the systems. And again, for software, for the accounting sorption, or not only sorption, for redox reaction, for dissolution, I advise you to use this FreakC modeling software from USGS, and it's open for everyone. It's quite useful and quite very often to use. They have a free, forum. If you have a question, you can just write the question and they will answer you. For the geochemical modeling, for transport modeling, it's very good thing. What else I need to say about sorption, that when we have some complex system, like for example soil, or even for clay, if they have some impurities, we need to account in sorption onto all minerals in one place. And there is two different approaches again. First is complex additivity, and second is generalized composite. Complex additivity means that, for example, you have some soil and you can understand which components do you have inside. And then, for example, here, goethite, smectite, feldspar, quartz, and then you understand which one is the most influence on my radionuclides of interest, or which one less. And if you can not count this option on less important component and just count it onto much important component. And when then you took the constant for all this reaction and calculating, even in Frixie, you can calculate, it's very easy. And second way, if you don't want to understand your particular system, which minerals are inside, you may just use it like general, like one black Okay, you can just generalize it and use it for experiment, make the absorption curve and calculate the constant, but the constant will not be assigned to any chemical reaction. It will be just assigned to this your generalized composite. It's again, this approach is maybe easier, but the predictive worth will be less than complex additivity, because if you don't want the composition of your mineral system, you may lose some reaction. For example, some dissolution reaction, you may not count it, or some transformation, but for very small range of experimental range, it may work. And the last chemical reactions that I want to talk to you, it's about solubility. I will not go to detail, but again, I just want to show you that different actinides with different oxidation state have a different solubility. And actinides 4-valent and 3-valent with high charge have a very low solubility, because it's very active to the hydrolyzation reaction. They very want to form solid phases. That's why the solubility is low. And for the pentavalent or hexavalent actinides, they usually have a high solubility. Why I'm talking about the solubility? Because sometimes in some predictive modeling, scientists may use the solubility line for the highest possible concentration of particular actinides. For example, as Germany, it's very popular to use this approach. They try to describe behavior of actinides in the salt disposal. They assume that they have neptunium-5, neptunium-6, plutonium-5, plutonium-6, and found this line and understand that, for example, for actinide 6, the solubility will almost 10 to the minus 6. It means that the concentration in solution may not be higher than 10 to the minus 6 mole per liter. And this level they use in the negative modeling. The highest concentration that is possible in the system will like solubility curve. It's sometimes useful and sometimes may help again for you to understand the highest concentrations that is possible in solution. And when you know all of this reaction, for example, for your system, you need the calculate and put it together. And finally, you will get the answer about the behavior of actinides or plutonium or other radionuclides in your natural system. And what is the most important thing for the today, for not today, but for the today or tomorrow, let's say, is the reactive transport. It's quite popular for today for example, some mining places, for the remediation territory, and for nuclear waste disposal. It's also very useful, and it's starting to to be applied for different scientific groups or for different reports for the creation of nuclear waste disposal. People use reactive transport. What this means? It's very simple, but not simple in the fact. But in principle, it's simple that you have a transport reaction, and then you add your chemical reaction to the transport. Transport usually may do some hydrogeologists, it's special people, it's not chemists. They may describe, for example, how water is move with the soil, with the rock, and they understand the transport dependencies. And then they put the chemical reaction on every step of the transport way and try to understand how our contaminants will put from the, for example, nuclear waste and will go to the environment. When we will do the reactive transport as best as we can, it will be very good, and that's why for today we are trying to do it in practice. And that's why I show you some in practice cases from the Russia. It's not so many cases for the reactive transport modeling, but I find someone and will show you. As maybe you know, in Russia, we have some such kind of waste disposal strategy when we put our liquid nuclear waste to the underground. We have 3 places where it's still going, in close to Krasnoyarsk, close to Tomsk, and close to Dimitrovgrad. And you see that there are different waste volume of injected. The most ejected places is Siberian chemical combine. And from our point of view, this strategy is very good because nuclear waste is unsafe in these places, but for the proof this strategy, we need to create the model of radionuclide transport underground in this condition. I will show you example particular in the, you see that it's Krasnoyarsk site. This is the places where nuclear waste are disposed. And if you go to the geology map, you can see that there is 2 horizons where nuclear waste are injected. The first horizons for the intermediate level waste, and the second horizon for the low level waste was injected. The geology of this place shows that it's very safe. This is some geology crack. I'm not geologist, I'm a chemist, yeah. But from the geology point of view, this horizon is very safe for the nuclear waste, and they did not move to here. And they may only move to one direction, and this moving is very slow. You see that it's only 5 or 6 meters per year, and it's only water. And the contaminants will go, of course, even less because they firstly absorbed by the host rock. And what was done in our institute, and you know that in the next week you will see the people from this institute. You may also discuss it with them. They did first of all, in this institute they produced a different computer code for some calculation, and they firstly produce computer code for reactive transport modeling, which they call GERA. This may calculate the geologist model. They may add chemical reaction to this model or made some other reactions, for example, some temperature reaction and so on. And first of all, they do a geological model for this place, and then they also try to do geofiltration, geomigration, and chemical reaction as well. Here's how it looks like. The model, you see that it's very big. Yeah, it's when I'm talking about chemistry, it's usually like a flask. And in case of the reactive transport, we need to make prediction for the kilometers, and its scale is much higher than for the usual chemical reaction. But our ability, mathematical ability, can help to us to calculate this. Calculate this. And here you see the how it looks like the predictive model for plutonium migration. And you see that plutonium is moving, but very, very slowly. It's 12,000 years from the starting of the injection. This is 102 years. You see that profile is moving, but very, very slowly. And that approve that there is migration will be, but it's very slow. And there is a proof that there is no vertical migration for the another horizons. And here's the chemical part. As I said, they use reactive transport model in this modeling. And you see that they predictive prediction for the concentration of nitrite and strontium in this injection well. And the green line is actual values, and red line is real mod, no, is modeling. And actually, when we're comparing the red one and the green one, we see that the principal profile is similar. I mean that when it's down, when it's high, it looks like similar. However, the absolute value is very different. And the reason for this, this means that hydrological part of this model is very good. They understand when the water will come faster, when it come slowly. But the chemical part is still need to be improving. And actually, in that time, the people using this model only simple KD approaches. And from my point of view, this is the most important reason why it's not all work perfectly. And right now, we are trying to make this model even better to induce it chemical reaction with a constant to assuming this chemical reaction. And finally, since it's my last slide, what I need to summarize for you that when you want to describe the behavior of or migration of actinides or radionuclides in the environmental, you need to do some things. You need to make sometimes laboratory experimental and strict condition which you may characterize, and you can understand which reaction may take place in this condition. Of course, you need to do to make a composition of observation well, which will give you information when radionuclide, or not only radionuclides, when pH which changes, when some inorganic cations and anions changes. And then you may to understand the main process that coming in this system, and then you can account it in the geomigrational model, and then your geomigration model will be reliable and accurate. Okay, and this is take-home message that accounting of chemical reaction, it's actually understandable. It should be working. It's still very difficult, but it's actually should working, and we need to move to this direction because it's very important to understand which particular processes are coming in the system, and we need to calculate for made predictive modeling for creation of safe nuclear waste disposal and so on. Question? Any other questions? Okay. And I just interesting, you are not chemist usually, yeah? Mostly you're not chemist. Oh, okay. Надо сделать.
Unajua break si mbali. Juu ni ile tu ya 5 minutes. Poa sana. Egira lodu. Poa sana. Mende. Oh. Iko Baba. No. Baba. Sasa mama akuja aseme muulize kama ana digrii anipigia niambie ipo. Usisahau. Sio kama hamna tutafute mahali pengine. Haya. Yatumika kuongea nipigia. Haya. Mwambie mama. Haiko mbali. Anakuja sasa. Hapi. Kweli. Tembea tu. Mimi sina kitu kutoka. Basi kaa chini basi. Kama ndio. Sisi kama iko. Wote ni yao. Iko. Kumbe anataka vita na pumu. Aende mbali. Hapo ziligi. Jaiona credit hapa sasa. Ndio hii simu hapa. Ndio huyo tu. Mama, kumbe sasa hivi nataka kutafuta unaacha simu. Eh? What? For what? Jambo gani? Wewe sasa namna gani? Yaani wewe unaniaibisha mbele ya mama. Nani anasema?
Hello.
Nani anasema? DK. Gani?
We are avoiding your Safaricom. Yes.
Jina yangu liko Olea. Sini class. Na kile kwa menini ikiwa jina yangu liko online. Nikifungua unatokea kwa hiyo screen yao. Hii ni screen yao huko. Ana watu wametoka class wametoka.
Wanakuwa wanakaa pale. Wataingia bado wameenda lunch.
Labda ni break ile ya 15 minutes. Hello, deal ni poa leo.
Anafaa kula nini? Wewe uende kuzunguka basi. Wewe kwani uko na nyumba? Nilikuwa nauliza uko na nyumba leo katika kutoka ile nyumba ya Sante ile. Wewe.
Mimi tajiri.
Najua nyumba yako najua. Najua nilikuwa sasa nauliza nyumba yako ni gani kakumbuka ile. Ndio kule. Naona ile nyumba hii naona kuna lata na ile mama. Ndio anakuwa kulala nyumba ya mabati na mtu ambaye alikuwa nyumba ya mawe. Ambaye anakuwa analala na nyumba ambayo imezoea nyumba ambayo anakuwa kulala nyumba ya mabati. Inasema ni Mungu.
Ndio huyu. Wapi alikuwa anaitwa nani yule jamaa?
Kwa mahindi? Hapana nani? Leo nikai juzi lakini ilikuwa ile ndoya. Wewe ndio ulituma ile ndoya?
Hapana. Nataka nikapande shamba langu.
Alafu pale Sombole nilipeleka mahindi juzi, mbegu ya mahindi ilikuwa ile ndoya.
Ndio ni nani?
James mwingine si wa ng'ombe wa mbuzi, ile ndoya.
Akachukua.
Hajachukua. Ni ya kwake.
Kama ipo, sikiliza. Mimi nakulipa pesa alafu ninaenda kuchukua hiyo kama ipo kule Sombole. Alafu wewe unakuja na kwake Jumanne, si kitu ni kile kile. Sasa nini mbaya unasumbua?
Hebu acha nione kama nani atakufikia hiyo nyumba mahali niliweka hizo mahindi.
Si haraka sana wewe kule malisi. Kule malisi. Ni kilo ngapi?
Paketi 7.
Paketi 7 sasa ndio maana ni
kilo 14.
Kilo 14.
Maana ni kilo.
Na heka moja na hiyo kwanza
wewe unapandaga
sasa mimi nimepikwa na mama nilikuwa huko Nairobi ananiambia hakika unasikia na mbele lakini tekeo na mangapi
kuna 831 na 7 mara 3 ni paketi 2
mbegu na yani kwa mfano
inakuelezea
shida yangu sijaenda shule lakini nitaenda mwakani
ninasema ile paketi pale kuna DK namba yake ni 80/31 na hiyo ingine paketi mbili iko 7 mara 777 mara 777 paketi mbili ni 777 paketi 5 ni 80/30
na hesabu kilo sasa
sio kilo kwa kila paketi imeandikwa kwa namba. Mimi sasa sio inamaanisha nini? Paketi moja ni kilo 2.
Hebu nione boss. hiyo picha yenyewe ndio kwa maji yangu. Samahani, unajua ulikuwa na
Nimeshamaliza.
umeshamaliza
Sasa uko hapa katikati.
kama ambao hiyo kwa mfano kule mimi ninapoishi na Dakar hii ambayo mimi naishi, yaani unaona hii mvua na hivi sasa hivi ukiweka mahindi hivi kei mvua ni mingi, lakini kule Dakar anapoishi mvua kio nyingi na hiyo ni sawa na hiyo bei
kwenye mkono.
Hao maboys wameenda pia wakubwa, ndio wadogo wadogo hapa. Wewe, kuja Leon shika. Leon. Shika ndio maji sheria kama ndio. Unajua baada ya endeni mpote. hiyo maboys wakubwa ndio wanaenda hapo chini tu.
Jana nilikuwa nauliza kita kila dua ungeenda.
Sasa hizi wako hapa. Oh yeah. Natokelezea. Na iko. Hiyo basi. Tunakuja. Tunakuja na mambogi sasa. Mweke chakula mingi. Adio wanaanza leo. Na watamaliza mbele yetu. Wewe ni nani? How are you? Sawa. Mbona uko red leo? Unaganga red hivyo? Mwili inachomeka. Unaiva. Yeah.